Okay, so now I'm re-recording part 1 of lecture 4 because I forgot to start the video in previous time. And so from lecture 3, I have some mistake there. At the end, I gave some homework, and one of the homework, the statements of the homework problems was not right. So let me just fix it. So what I wrote was, I wrote this like an operation start from minus k to k to r given by a star b equals a plus b over 1 plus kab. But this is wrong. So this is wrong. And the right, so this is wrong. And the right one is this one. So star from here k is a positive real number. Is star from minus 1 over k to 1 over k to r, and the operation is given by a star b equals a plus b over 1 plus k squared ab. And this is the wrong, this is the right operation where a and b are in this interval. So this is the right one. Okay. So this is from the previous time. So now I'm going to start the big topic, one of the big topics of this course, and the big topic is in algebra, which is module theory. Module theory is the theory of the linear algebra over rings. So it's a generalization of standard linear algebra, which is over fields. So this is linear algebra over rings. And I'll use the following notation: a commutative CRWU. I don't know a standard abbreviation, but I've used the most direct one. So this is commutative ring with unity. To recap, a commutative ring with unity is a space where we can add, subtract, and multiply things, but it's not necessary to be able to divide. So for instance, integers are commutative ring with unity, and rational numbers or real numbers, they are filled. There we can also divide non-zero elements. So let's define what a module is. So definition. Let R be a commutative ring with unity. And V with operation plus, minus. Later I will use only V because operations will be assumed to be this one. B and abelian or commutative group. And star from R times V to V be a scalar multiplication. i.e., it satisfies the following properties. It satisfies the following. First, it's some kind of associative, but with respect to both sets. So for any scalars, so for any lambda and mu in R, we have, and any V in the big V, we have that lambda times R. Oh, I forgot. So the operations here will be with, so these operations on V are different than those on R, but they're usually, we usually don't write subscripts, and it's understood from the context where we do addition on R or addition on V. But for this definition, now we use subscripts. So when we multiply two elements of R and then do a scalar multiplication with V, we get lambda times scalar multiplication with the scalar multiplication of mu with V. So in some sense, we can remove brackets when we have operation multiplication of numbers and then of vectors. The second one is now two distributive laws hold. So for the second one is now two distributive laws hold. So for all lambda and mu in R and all V in V, if we have lambda plus mu times V, this is equal to, so this is operation in R, and we have lambda times scalar multiplied with V plus operation in R in V, so mu times V. We have so this is distribution over addition of scalars. We have distribution over addition of vectors. So for any lambda in R and any U and W in V, we have lambda times V plus mu, V plus W is lambda times V addition in the vector in the module mu times V. And finally, we have the unit condition for all V in V, the identity, the unit element 1 of R multiplied by V gives V. Now, all these axioms combined with axioms for V give some natural way of doing operations on the module. And we call we say that V is a module over R or V is an R module if R is a vector space, is a field. V is called a vector space. V is called a vector space. Vector space over R. So the theory of anything that is true for modules is true for vector spaces. So we will do a little bit more generalized theory. And to finish the notation, so the elements of R are called scalars, and the elements of V are called vectors. Even in module theory, so they are called vectors in linear algebra, standard algebra over field, but in module theory they are also called vectors as well. Okay, so this is the definition of a module and the common language. And so let's proceed with some examples. Let me clear the board. So let me give some examples. We will fix some commutative ring R. So let R be commutative ring with unity. And take some integers and some natural numbers. Even zeros are allowed. In all of the examples, if one of the numbers is zero, we get the zero vector space, which I define shortly. So first of all, we get the space of tuples, what is usually understood in, for example, in computer science as a vector. So Rn is an R module with the following operations. So addition is given as the following. So A1 AN plus B1 BN is defined by A1 plus B1 and AN plus BN. And the standard addition of tuples. So here, OA, I, and BI are in R. And multiplication is given component-wise, so lambda times A1. Usually this sign is omitted, but I will write it here. Is by definition lambda A1 plus, sorry, not plus. This is tuple. So, comma, to lambda an. Again here, lambda is, and all the i's are in R. So lambda is in R, and ai is in R. So we have the space of tuples, which are, as I said, called vectors usually, but here in mathematics we understand vector as something more abstract. So vector is element of an arbitrary vector space, not only of space of tuples. We also have the space of matrices. So A, M, N of R is an R module. Now that this is an R module, I'm not going to check this, but anybody can check that. There are 4 axioms for addition, that is a Abelian group, and 4 axioms for scalar multiplication. The associative rule, the 2 distributive, and the 1 multiplied by distinct equals it again the same result. So we have an R module, and we have 2 matrices. So if we have 2 matrices, A11 to AMN, and multiply by add to it B11 to BMN. This is by definition the sum of the components. So A11 plus B11 to AMN plus BMN. For Aij, Bij in R. And here as well, scalar multiplication is given component twice. So lambda times A1, and I have matrix, not a vector. A11 AMN is given by lambda the first element and 2 lambda the last element. Okay. So we have 2 examples for now. Let me give 2 more. So we have the 0 ring, the 0 vector space. So the 0 vector space sorry, the 0 module vector space is when I is a field. The 0 module, it has only one element 0, and any kind of operation always returns 0. The 0 module denoted also by 0 without brackets. Space of vectors with length 0 or matrices when the rows or columns are 0 is also 0 module. But yeah, this is also the trivial module in some sense. Now, some interesting case which will be important in future when we form chain spaces are the free module. So free module. So let S yeah, it can be defined for infinite set. I will define first for finite set. So S be a finite set. Be a finite set. So these are some arbitrarily elements. They can be anything. They can be apples and oranges. Doesn't matter. Be a finite set. And so free. This is notation. Free RFS is the module of all formal linear combinations of the elements of S. And it's called so it's called the free R module over, I'm not sure, on or generated on the set. Let me write on the set S. Okay, this thing here. So this is the space of linear combinations. So how do we define operations? So addition, we define addition as follows. Addition is defined the following way. So if we have two linear combinations, so lambda 1 E1 plus lambda 2 lambda n En. So the set, I didn't write it, but the free module is just the set of all these combinations where lambda 1 to lambda n are arbitrary. And so if you have V equals this thing and W equals mu1 E1 plus mu n En, then their sum is just the sum of their coefficients, again multiplied by the elements, so-called basis elements. So V plus W equals lambda 1 plus mu1 times E1 and until lambda n plus mu n times En. And scalar multiplication is again defined in some sense component like scalar multiplication. So here we have addition. So if V is again lambda 1 E1 plus lambda En and mu is in R, then mu times V is by definition lambda mu times lambda 1 E1 plus mu times lambda n En. So we are multiplying all the coefficients lambda 1 to lambda n by mu. This is the free module. It's easy to check that it satisfies the axiom of a module, the 8 conditions. Okay, let me give some note here. So note. This is for again for this case, for the free module. S can be a set S can be infinite, in which case we take only the final linear combinations. In which case we take only the finite linear combinations. So if it has infinite number of elements, any linear combination is a finite one. So it can be, for example, lambda 1 E1, yeah, plus lambda 3 E3 plus lambda 5 E5 if we have 3 elements E1 to E5. And everybody knows that some a space which is a free space generated by a finite infinite basis, but I assume most of you don't know this framing, so let me write it down. So for example, for instance, if S is the set of this kind of formal elements, 1x, x squared, and so on, xn. These are all the monomials, is the set of monomials. Then the free module is denoted by x, and this is the set of single variable polynomials. Note that we have an infinite element, but you only take finite combinations. So polynomials, they have their finite cut from the space of all formal combinations. If we are allowed to take infinite combinations, we get here the space of formal power series, but we are not interested in that. We're interested in the space of polynomials. Okay. So now let's go to the. Okay, I will delete that because I want to write a long definition. So let me now go to the one of the most important. Yeah, the most important notions. So I will talk about sets of vectors, and it can be infinite, but for simplicity, I'll talk about finite subsets of vectors. So definition. let, as usual, R be a commutative ring with unity. Commutative ring with unity. And V be an R module. And take a finite set of vectors. So, so let's S equals E1 to En is a subset of V. So we say that we can state it for the whole set S for the vectors. I will say for the vectors because it's usually how it's framed. We say that the following. So that not E1, let me write it there. V1 here. That these n vectors. So this is one. V1 to Vn are linearly independent if the only trivial combination giving the zero vector is the zero combination. So this is written as follows. So for any coefficients lambda 1 to lambda n in R, if lambda 1 elan plus lambda, then all of the coefficients are zero. No, this is V. V1 lambda 1 to lambda n are 0. The opposite notion is the notion of linear dependence. So if we take the negation of that, so V1 to Vn are linearly independent, also linearly dependent. If so, when you take negation of universal property, it takes negation becomes existence, and the rest is the negation. So there exists lambda 1, lambda n in R. And negation of implication is that this is true and this is not true. So there exist such lambdas that these are not zero. Some of them is not zero. So the tuple lambda n1 to lambda n is not the zero pair. So at least one of them is not zero. And their combination is zero. Okay. I'll talk about a bit. This is the true definition of linear dependence. In the vectors of space theory, when the ring is a field, the base ring, so-called R, is field, it can be stated in a different way, but not in general. But let me just finish the definition and give some example. I'll talk about this. So 3, we say that V1 to Vn span the whole set, span V, if any vector can be expressed as a linear combination. So any vector y no, let me write this w. Any vector w in R in V, sorry, there exists lambda 1 to lambda n in R such that lambda 1 V1 plus lambda n Vn equals to double. And V1 and to Vn are bases of V for not R, for if they are linearly independent and span V. If they are linearly independent and span V. Okay. Now, before talking about this, giving some remark about linear dependence, let me give examples of bases. Okay. I'll clear the board. So this is the definition. These are the four main notions about sets of vectors. Okay. Examples. Oh, it's wet. Let me just dry it a little bit. Oh, sorry. Yeah. Let me now give example of linear dependence and how it differs if the ring is a field or not. So let R be the set of integers or the set of rational numbers. I just get two sets. This is a field, this is not a field. And consider the two vectors. And so first define the vector space. So V is R squared. Even first define the vector space. So V is R squared. Even R will work, but let's say R squared. Oh, sorry, R squared. And take V two vectors. V1 equals to 2, 0, and 3, 0. V2 equals to 3, 0. Then they are linearly dependent. Then we have the following. Then lambda. So we have that 3 times V1 minus 2 times V2 equals the 0 vector. Hence, V1 and V2 are linearly dependent. Okay? They're linearly dependent. However, there is a difference whether we work on integers or rational numbers. So if you work on rational numbers, if R equals Q, then one of them can be expressed by the other. So V1 is minus 2/3 of V2. So one of them can be expressed by the other. However, if R equals Z, then no one of them is expressed, it's a multiple of the other. So no one of these two vectors of V1, V2 is a multiple of the other. And this, in fact, is a general feature. So in general, if the ring is not a field, it might not be represented as a multiple, as a linear combination of the others. So let me erase everything so we have a clear board and gives the remark rigorously. So we have the following remark. So if if R is a field and V is a vector space over R, so a module but over field, so it's a vector space. Then we have the following. So if V1 to Vn are linearly dependent, then they are at least one of them is expressed by a linear combination of the others. Then one of them is a linear combination of the others. Indeed, so indeed, they are linearly dependent. Let lambda 1 to lambda n are in R such that the combination is not 0, is not the 0, 1, and they'll sum up to 0, so lambda 1 v1 plus lambda n. So we have the 0 linear combination. So since this is not the 0 vector, not the 0 tuple, at least one of them is non-zero. So let lambda y is not 0 for some y in this interval. And now, because we are in field, any non-zero element is invertible. And there we have the following, that if we rearrange this, we get lambda, the sum of all lambda g, so all g from 1 to n, where g does not equal to e, of lambda j v j is equal to minus lambda I v I. And because this is non-zero element in field, we can divide it, and this not can be done in a if y was only r was only commutative ring with unity. But here we can divide it, and so we get vi is the following sum of j from 1 to n, j doesn't equal e, of minus lambda j over lambda I vj. Okay. And so, oh, sorry, it should be, because in the initial recording it was everywhere mu, so I will change lambdas to mu. Nothing changes the letter. So if we define, if we define lambda j equals minus mu j over mu I for g different than e, then we have vg is the linear combination g from 1 to n, g doesn't equal I of lambda j vg. So if we are on a field, the equivalence of some set of vectors be linearly dependent is that one of them is expressed by the others. But as we saw, this is not really general modules over commutative rings with unity. So we prefer the definition, this definition here. And also it is good because it's symmetric in the arguments. This one here is we have to choose some I and express from the others, but this one doesn't have such choice of index and combinations and like that. And with that, I finish this part of lecture 4.1. I forgot to record when I gave it initially.